According to the National Electrical Code, or NEC, metal-clad cables, or NEC cables, have specific insulation requirements when placed in enclosed spaces containing thermal insulation. Article 330.11 C addresses this scenario. NEC cables are permitted in concealed spaces filled with loose thermal insulation, provided the insulation is non-flammable or the cables themselves are listed for this specific condition. Article 330.15 C states that NEC cables can be installed in concealed spaces filled with spray-on foam insulation if the insulation is listed for this condition and the cables are rated for the temperature. If the NEC cables are installed in an enclosed space containing thermal insulation not specifically listed for such installations, derating factors must be applied to the cable's ampacity. The specific derating factors depend on both the type of insulation used and the cable's operating temperature. Consider a scenario where NEC cables are installed within a bar joist space and subsequently covered with spray-on insulation. If the spray-on insulation is explicitly listed for use with NEC cables, then no derating is required. However, if the insulation is not listed for use with NEC cables, derating factors become mandatory. The specific derating factors will vary based on the insulation type and the operating temperature of the cables. Consulting with both the insulation manufacturer and referencing the electrical code is always recommended. This ensures that NEC cables are installed in full compliance with all applicable regulations and standards. As a good practice, always label the cables with their derated ampacity, especially when derating is necessary. Let's delve into a more detailed explanation of ampacity derating for conductors in insulated environments. When conductors, including NEC cables, are installed in environments where heat dissipation is hindered, such as within thermal insulation, their ability to carry current is reduced. This reduction is known as ampacity derating. The NEC provides tables and guidelines to determine the appropriate derating factors based on several factors. Firstly, the type of insulation surrounding the conductor significantly impacts the derating requirements. Different insulation materials have varying thermal conductivities, affecting how easily heat can dissipate. For example, some spray foam insulations can trap heat more effectively than loose fill insulation, leading to a greater need for derating. Secondly, the ambient temperature in the vicinity of the conductors plays a crucial role. Higher ambient temperatures reduce the temperature difference between the conductor and its surroundings, decreasing the conductor's ability to dissipate heat. The NEC provides correction factors for ampacity based on ambient temperatures exceeding 30 degrees Celsius or 86 degrees Fahrenheit. Thirdly, the number of current-carrying conductors in a raceway or cable affects the overall heat generated. When multiple conductors are bundled together, the heat from each conductor contributes to the overall temperature rise, necessitating derating to prevent overheating. NEC Table 310.15 B3 provides adjustment factors for the number of current-carrying conductors. To determine the appropriate ampacity derating, you must first identify the allowable ampacity of the conductor based on its size and insulation type, as specified in NEC Table 310.16. Then apply the appropriate correction factors for ambient temperature and the number of current-carrying conductors. If the conductors are installed in an insulated environment not specifically addressed in the NEC, it may be necessary to consult with a qualified electrical engineer or testing laboratory to determine the appropriate derating factors. In such cases, thermal modeling or testing may be required to accurately assess the heat dissipation characteristics of the installation. Always prioritize safety and compliance with the NEC when installing electrical conductors in insulated environments. Failure to properly derate conductors can lead to overheating, insulation breakdown, and potentially electrical fires. Remember to document all derating calculations and label the conductors accordingly to ensure the safety of future maintenance personnel. Here are some specific examples of how derating factors might be applied in different scenarios. Firstly, consider a situation where 3 current-carrying conductors are installed in an NEC cable that is embedded in spray foam insulation not listed for use with electrical cables. The conductors are rated for 90 degrees Celsius, or 194 degrees Fahrenheit, and the ambient temperature is 35 degrees Celsius, or 95 degrees Fahrenheit. According to NEC Table 310.16, a 12 American wire gauge (AUG) copper conductor with 90 degrees Celsius insulation has an ampacity of 30 amps. However, due to the ambient temperature exceeding 30 degrees Celsius, a correction factor of 0.91 must be applied, resulting in a derated ampacity of 27.3 amps. Additionally, since there are 3 current-carrying conductors in the cable, an adjustment factor of 0.80 must be applied, further reducing the ampacity to 21.84 amps. Therefore, the final derated ampacity of the 12 AWG conductor in this scenario is 21.84 amps. Secondly, imagine a scenario where 6 current-carrying conductors are installed in a raceway that is partially filled with loose-fill insulation. The conductors are rated for 75 degrees Celsius, or 167 degrees Fahrenheit, and the ambient temperature is 25 degrees Celsius, or 77 degrees Fahrenheit. According to NEC Table 310.16, a 10 AWG copper conductor with 75 degrees Celsius insulation has an ampacity of 30 amps. Since the ambient temperature is below 30 degrees Celsius, no temperature correction factor is required. However, due to the presence of 6 current-carrying conductors in the raceway, an adjustment factor of 0.80 must be applied, resulting in a derated ampacity of 24 amps. Therefore, the final derated ampacity of the 10 AWG conductor in this scenario is 24 amps. Thirdly, consider a situation where MC cables are installed in a boudoir space and covered with spray-on insulation that is specifically listed for use with electrical cables. In this case, no derating is required, provided that the conductors are operated within their rated temperature limits and the insulation is installed in accordance with the manufacturer's instructions. However, it is still recommended to verify the installation with a qualified electrical inspector to ensure compliance with all applicable codes and standards. In addition to ampacity derating, it is also important to consider the voltage drop in conductors, especially in long runs or when supplying sensitive electronic equipment. Voltage drop occurs when the voltage at the load is lower than the voltage at the source due to the impedance of the conductors. Excessive voltage drop can cause equipment malfunction, reduce performance, and even damage. The NEC recommends limiting the voltage drop to no more than 3% for branch circuits and 5% for feeders. To calculate voltage drop, you need to know the conductor length, the current flowing through the conductor, and the conductor's impedance. The NEC provides tables and formulas for calculating voltage drop based on these factors. If the calculated voltage drop exceeds the recommended limits, you may need to increase the conductor size or reduce the length of the run. In some cases, it may be necessary to install a voltage regulator or other voltage boosting device to maintain the proper voltage at the load. Another important consideration is the proper grounding and bonding of electrical systems. Grounding and bonding are essential for protecting against electrical shock and preventing equipment damage. Grounding provides a low impedance path for fault current to flow back to the source, allowing overcurrent protective devices to quickly trip and clear the fault. Bonding ensures that all metal parts of the electrical system are electrically connected, minimizing the potential for voltage differences and shock hazards. The NEC specifies detailed requirements for grounding and bonding, including the size and type of grounding and bonding conductors, the methods for connecting grounding electrodes, and the requirements for bonding metal enclosures and equipment. It is crucial to follow these requirements carefully to ensure the safety and reliability of the electrical system. Furthermore, surge protection is an increasingly important consideration for protecting electronic equipment from voltage surges caused by lightning, utility switching, and other transient events. Voltage surges can damage sensitive electronic components, leading to equipment failure and data loss. Surge protective devices, or SPDs, are designed to divert surge current away from protected equipment, minimizing the risk of damage. NEC requires SPD to be installed in certain locations, such as service entrances and panel boards, and recommends their use for protecting sensitive electronic equipment throughout the electrical system. SPD are available in various types and sizes depending on the application and the level of protection required. When selecting SPD, it is important to consider their voltage rating, surge current capacity, and protection level. Regular inspection and testing of SPD are also essential to ensure their continued effectiveness. Moreover, arc fault circuit interrupters, or FSIs, are another important safety device for protecting against electrical fires. FSIs are designed to detect arc faults, which are dangerous electrical conditions that can cause fires. Arc faults can occur due to damaged wiring, loose connections, or faulty appliances. When an arc fault is detected, the FSI quickly trips the circuit, interrupting the flow of electricity and preventing a fire. The NEC requires FSIs to be installed in branch circuits supplying bedrooms, living rooms, and other areas where arc faults are more likely to occur. FSIs are available in various types, including branch circuit FSIs, combination FSIs, and outlet branch circuit FSIs. Regular testing of FSIs is recommended to ensure their proper operation. In addition to these safety devices, it is also important to follow safe work practices when working with electricity. Always de-energize circuits before working on them and use appropriate personal protective equipment, or PPE, such as insulated gloves and safety glasses. Never work on electrical equipment when you are wet or tired. Be aware of the potential hazards of electricity and take precautions to avoid electrical shock and burns. Regular training and continuing education are essential for staying up to date on the latest electrical codes, standards, and safety practices. Consider attending electrical safety courses and workshops to enhance your knowledge and skills. Stay informed about changes to the NEC and other relevant regulations, and always follow the manufacturer's instructions when installing and maintaining electrical equipment. By following these guidelines, you can help ensure the safety and reliability of electrical systems and protect yourself and others from electrical hazards.